In this set of PowerPoints, we're going to talk about the binomial probability distribution. The requirements for a binomial distribution, or the things that define the probability distribution as a binomial probability distribution, are summarized by the acronym FITS. There have to be a fixed number of trials. Have to have independence. That means what happens on one trial doesn't affect what happens in the next. Two possible outcomes. It's a binomial. And you get success or failure, yes or no, male or female, defective, non-defective, so on. And the same probability of a success for each observation. So here's an example of a binomial variable, flipping a coin. There are a fixed number of trials. What I'm talking about here is I'm going to flip a coin 3 times. Then I could repeatedly do that, flip the coin 3 times again, then 3 times again, and then make a probability distribution on the possible things that can happen when I flip a coin 3 times. For example, I could get 3 heads in a row, 3 tails in a row, 2 tails and then a head, and so on. But it's based on a fixed number of trials, in this case, 3. Independence, what happens on one flip, the coin doesn't affect what happens on the next flip. There isn't any memory here. 2 possible outcomes, in this case, heads or tails. And the same probabilities. Every time you flip the coin, assuming it's a fair coin, there's a 50% or 0.5 chance that a head will occur. Okay, here's something that's not a binomial variable. Drawing aces from a 52-card deck. On the first draw, the probability of drawing an ace from the deck is 4 out of 52. On the second draw, the probabilities depend on what happened on the first draw. If you had an ace the first time, there's 51 cards left, and only 3 of them are aces, so the probability is 3 out of 51. So it's not independent. What happened in one trial affects what happens in the second. We could also have not gotten an ace the first time, and that would also impact what happens on the second draw. And the probability changes. It's now 4 out of 51. Let's go back to the flipping of a coin 3 times. We're going to draw something called a tree diagram. So we just have the first flip of the coin. We can get a head or a tail, and the probabilities associated with each are 0.5. Again, assuming we have a fair coin. So that's the first flip. And here's the possible things that can happen on the second flip. If we had a head the first time, it can be a head or a tail the next time. The probabilities stay the same. Doesn't make any difference what you had the first time. And if you had gotten a tail going along the lower branch, of course you could have gotten a head or a tail on the second trial that way as well. So now we're going to flip the coin a third time. And so we could have, at the very top, had 3 heads in a row, followed by the next one, head, head, tail. So we're just going to follow along the branches there and summarize all the possible sequences. We could have had 3 heads in a row, 2 heads and then a tail, a head, a tail, and a head, and so on. And then we can compute the probability of each of those sequences by multiplying the probabilities along each path in the tree diagram. So for the top one, it's 0.5 times 0.5 times 0.5. That's 0.125. Now in this case, since all the probabilities are 0.5, we're going to have 0.125 or 1/8 for each of the 8 possible sequences. Now if we'd had an unfair coin that was 60-40, then we would be multiplying some combination of 0.6s and 0.4s, and those probabilities wouldn't all be the same when we got over the right-hand side. But we're going to take these sequences and their probabilities and use them to construct a probability distribution, which is just a list of all the possible values of x and the probabilities associated with each. So if we flip a coin 3 times and let x be the number of heads, we can either get 0, 1, 2, or 3 heads in 3 flips. So the probability of 0 heads, we just go down. There's only one time that happens. It's the bottom set of branches, tail, tail, tail. And we can just read the probability straight off of there, 0.125. Now the probability of exactly 1 head, well, that occurs 3 times, and you can see I've got it color-coded there, a head and 2 tails, a tail, head, tail, and 2 tails followed by a head. Each one of those has 1 head. Each one has a probability of 0.125. So we'll just add those together and get 0.375 as the probability we'll get exactly 1 head. Similarly, with 2 heads, we have 3 possible sequences that have 2 heads apiece. We'll add those together and get 0.375. And with 3 heads, there's only one possibility, 3 heads in a row. We've got the 0.125. And of course, this is a probability distribution, which is pretty close to the same thing as a relative frequency distribution. And so the sum will always be 1. So for our probability distribution, again, we have, just reviewing here, a list of all the possible values of x, the number of heads, 0, 1, 2, and 3, and then the probability associated with each value of x. And it's a probability distribution, so it sums to 1. Okay, so now suppose we're going to flip the coin 10 times. How would we go about obtaining the binomial distribution? Our first option is just to get a really big piece of paper and start drawing. That'd take a while. Fortunately, we can use a table that's already been prepared for us called a binomial table, and we use that to obtain the probabilities. You can get that binomial table off a blackboard, or if you were in the daytime class, I handed those out. So here's just a piece of the table, and you can see here that I've got n at this part of the table. N could be 2 or 3. We did 3 flips, so we go down to n equal 3. And then the possible number of heads, 0, 1, 2, or 3. Go up to the top and get the probability of a head on each flip. That was 0.5. And then here we've got the probabilities. So basically we have our probability distribution. Over on the left we've got 0, 1, 2, and 3, and then our probabilities. So if we know the sample size, then we can just read off the possible numbers and the probabilities associated with each. We also know the probabilities for each trial. So I'll let you look at that for a second. So the probability an IT guy is a geek is 0.70. I obtained that scientifically. So we're going to construct a binomial distribution for a sample of 8 IT guys. So I went down on the table until I got to an n of 8. You can see I have all the possibilities there, 0, 1, 2, 3, 4, 5, 6, 7, and 8. I don't have the whole table here, but I've drawn a square around that portion of the table that's associated with the probability of 0.7. Just look at your table and make sure you can get to the same point. And here's a graph of the distribution. I just took all the possible values, 0, 1, 2, 3, 4, 5, 6, 7, and 8, and drew a line. It's a discrete value, so I'm only going to have a line associated with each value and just draw it up to what the probability is. Now I'm going to go back to the table. Now I've just moved the probabilities over next to the possible values. That's my probability distribution. A list of all the possible values of x, 0, 1, 2, 3, 4, 5, 6, 7, and 8, and the probabilities associated with each, the 0, 0, 0, 1, down through the 0.0576. If we added those up, by the way, all those probabilities, we would of course get 1, unless there's some rounding in the tables. But we're always going to get 1, or if you're looking at the table, 0.999 or something like that. But we'll just assume that it's 1. It would be if we carried it out far enough. Now we can ask questions like, what's the probability of getting exactly 3 geeks? So just go down to 3 and read across. That's 0.0467. then the probability of at least one geek. Well, we could just start adding at 1 and go all the way down to 8, add those probabilities, 0.0012, 0.0100, and just all the way to the bottom, add those up. Or we can make use of the fact that the sum of all those probabilities is 1, and the only time you don't have at least one geek is when you have 0 geeks. So we can subtract that probability, the 0.0001, from 1 to get the probability of at least one geek. It's 0.999. So the probability of at least 6 geeks, we'll start at 6. 6 is at least 6, 7, and 8, and just add those probabilities, the 2965, the 1977, and the 0576. And I got that to be 0.5518, about 55%. So let's look at what another distribution. We have 30% of people use a toothbrush for something other than brushing their teeth. So in a random sample of 6 people, what's the likelihood, this is where we're going to ask some questions in a second, use a toothbrush for something other than brushing their teeth. So first I've got the probability distribution here, a list of all the possible values of 6, 0, 1, 2, 3, 4, 5, and 6, and the probabilities associated with each. Go back to your binomial table and make sure that you can get to the right spot here, and you can read and write that probability distribution using the binomial table. And once I'm to this point, then I can start asking questions like, what's the probability that exactly 2 use a toothbrush for something other than brushing their teeth? You can just read that off. It's 0.3241. Then the probability that we have more than 4. So that doesn't include 4 because 4 is not more than 4. So we'll add the 0.0102 and the 0.0007. I got that to be 0.0109. Between 3 and 6 inclusive, that just means the inclusive means that we're going to include 3 and 6. So we're going to start at the 1852 and go down to the 0007 and just add those up. I got that to be 0.2556. Now between 2 and 5 exclusive, that means don't include the 2 and the 5. So we're going to again start with 3, which is 0.81852, and then go down to 4, which is 0.0595. So we've got everything between 2 and 5, but not 2 and 5 because we're excluding those. So it's really just the probability of 3 and 4. Adding those together, we got 0.2447. Let's have a little preview of what's to come. Basically, what's going to come when we get to that move from sample to population, or inferential statistics. So we asked 6 randomly selected people, and all 6 use a toothbrush for something other than brushing their teeth. And you can see down here that probability is 0.0007. That's pretty small. In fact, it's so small that we might question whether or not our original presumption of 30% is true. In fact, if we had 6 out of 6, we might think the probability is a little bit higher than 0.3 in the entire population. So if we think of that 30% as a hypothesis, then we go out and take a sample. All 6 are using a toothbrush. Now we've raised a question about that hypothesis. And in fact, we might, and later on will, conclude that the real population percentage really we'll look at proportions, and we'll say is the true population proportion greater than 0.3. That's what we will conclude, because it's almost never going to happen that we'll get 6 out of 6 if it's really only 0.3 or 30% of the population. You might want to read through that a couple of times. It's going to be the rationale that we use for a lot of the class. Placing under simulations on Blackboard, it's the one that comes from Coventry for the binomial probability distribution. And what you can do over on the left-hand side, where I've got, it's in the kind of light bluish green stuff here, I've got n is 4, p is 0.1, and so on. You can look at the a and b and so on. That's going to give you values that you could get off of the binomial table. What I really want to do is just use this simulation to show you some basic characteristics of the binomial distribution and what happens when you change the sample size or the value of p. So what I have right here is a sample size of 4 and a p of 0.1, and then just a graph of that binomial probability distribution. And you can see that it's a skewed graph, skewed down to the right. Let's see what happens if we increase the sample size to 8. Still skewed. 12. Whoop, changed the wrong thing. That was 0.1, and that's 12. Skewed, but look, we're getting a little bit of a tail on the other side. Now let's go up to 40. It's starting to look like a bell curve now, and that's one of the things I want you to see, is that when the sample size is increased, the binomial distribution, even one that was highly skewed, starts to looking like a bell curve. And if I get to 100 here, I keep changing the wrong 3 there. That's 0.1. It's the sample size that I want to change. And you can see now that that looks like a bell curve. Now we'll be talking tomorrow about the bell curve, but what I want you to notice here is that even something that's not a bell curve, if you take a large enough sample, we're going to be able to use the bell curve and the characteristics of the bell curve to describe the distribution of data. So let me go back to a smaller sample size of, let's go to 8. Again, that looks pretty skewed. Now instead of changing the sample size, I'm going to change the probability of success, and I want to raise that up to 0.2. You can see the same kind of progression starting here. That as we raise that probability, we start to look more and more like a normal distribution. At least until we get to a probability of 0.5. Once we get beyond 0.5, I'm going to go to 0.6, you can see it starts now to skew again, but in the opposite direction as we had in small sample sizes. Well, anyway, I go back to 0.5 here. There's 2 factors here then that affect the shape of the distribution, and specifically for our interests, in the convergence of that distribution from something that's very skewed to something that looks like a bell curve. One is that you raise the sample size. Remember, we went from 4 to 8 to 40 on up to, I think it was 100 a minute ago. The other thing that affects that is the value of p, the chance of success in the population. And as we got closer to 0.5, the binomial distribution became to look more and more like a bell curve. That phenomenon won't be just a factor associated with the binomial probability distribution. It's that convergence to a bell curve for a variety of distributions, skewed or otherwise, and that convergence of those things to a bell distribution or to a bell curve, a normal distribution. It's going to be pretty important to what we do with inferential statistics.